Design of reinforced concrete rectangular beams. Sample problem. Determine the width, depth, and the number of number 9 steel bars for the beam shown. We have here a simply supported beam with a uniformly distributed load, WU, and we are to look for the width, the height, and the number of number 9 steel bars which can satisfy the load requirements. Okay? Here, the beam length is 26 feet. The dead load excluding the beam weight is 1.2 kip per foot. The live load is 2.5 kip per foot. FC prime 4,000 psi, Fy 60,000 psi, and the unit weight of concrete is 150 pounds per cubic foot. Here's the solution. The first step is to estimate the beam dimensions and weight. Okay? So to estimate it, we have to assume that the height of the beam is 10% of the beam length. So the beam length is 26 feet. So 10% of that is 2.6. Okay? And then multiply it by 12 so that you can convert it into inches. So that will be 31.2. But since 31.2 is so hard to fabricate, no, in terms of the formworks, we have to round it off into the nearest inches. So say 32 inches. In here, in the formula in Excel, the formula is round up. So the 31.2 is rounded up to 32 inches. Okay? Now, the section of the beam will look something like this. Okay? You have your stirrups. Okay? And then, here are your main bars. Let's say, for the sake of example or illustration, let's just have 2. So, here will be your concrete cover. Okay? We need this covering in order to protect the steel from corrosion. And the standard covering is 1 1/2 inch. So 1 1/2 inch. And for the stirrups, normally, if not given, the stirrups should be number 3. Number 3. Or 3/8 of an inch. Okay? And your D now shall be calculated from the centroid of this steel, the main bar, to the outermost compression fiber. Okay? So therefore, what is then your measurement now? No? We know that the diameter of the rebar is number 9 as stated in the problem. So 1 1/8, and diameter of stirrup is 3/8, and the covering is 1 1/2. Your D shall be, to illustrate it, we have the H which is 32 inches. That will be deducted by the covering, by the diameter of stirrups, and by the diameter of main bar, let's say DB, over 2, because this one is at the center. Okay? So 32 minus covering. Okay? So here in the formula, we have 32 minus covering, which is cell number 36. And then next is the diameter of the stirrup and the diameter of main bar divided by 2. That's why there is a 2 here. Okay? For those who want to really trace the formula, you can pause the video now and trace the formulas using this formula bar. Okay, so you can then now have your D based on the assumed value of H. Next is to assume the width of the beam, and the beam width should be 50% within 50% of the height. So the height is 32 inches. 50% of that will be obviously 16 inches. Just in case there is a decimal place, then you have to round it off to the nearest whole inch, so that it will not be difficult for the formworks fabricator to fabricate for the formworks of your beam. Alright, so after that, we now have to estimate the beam weight. To estimate the beam weight, this is just simply the area times the unit weight of concrete. The unit weight of concrete is given as 150 pounds per cubic foot. And the area is the area of the B times your H. Okay, B times H. So let me rewrite the formula for a better understanding. So that would be B times H times unit weight of concrete. And just be careful with the units. No, B and H are in terms of inches, and the unit weight is in terms of feet. So therefore, divide this one by 12 by 12, because there are 2 inches units here. And divide everything also by 1000, because the unit here is in terms of pound, so that you can get an answer of 0.533 kip per foot. Okay, so after solving the three, the height, the width, and the beam weight, we can now compute for WU and MU. Okay, so how do you compute WU? WU can be computed from the load combination of 1.2 dead load plus 1.6 live load. But your dead load should be the given dead load plus the weight of the beam. Okay, so what is the given dead load? The given dead load is 1.2. Okay, let me just rewrite it here. So 1.2 times the given dead load, which is 1.2, plus the weight of the beam, which is 0.533, plus 1.6 times the live load, which is given as 2.5. So we have 2.5, and we can generate this answer. Then for MU, we can solve MU by using the formula for simple beam, WL squared over 8. If you don't know the formula, you can also do a shear and moment diagram. So to do the shear and moment diagram, okay, let me redraw the beam. This is a simply supported beam, and you have WU equivalent to 6.08 kip per foot. And let us try to solve the value of the maximum moment. So first, we draw the shear diagram. Okay, so for the shear diagram, we need to know the reactions. But first, we have to solve for the resultant of this. The resultant will be, if this is your L, the resultant will be WUL. Okay? And the reactions will be divided into the two supports. So that will be WUL over 2. here WUL over 2. Okay? And to get the shear diagram, there is a concentrated force here. So you move upward by a value of WL over 2. And then this one is 0 degree. This is a horizontal line, so this is 0 degree. So the shear will be on the first degree. The shear is a first degree curve. So a first degree curve is a straight line with a slope. So the slope goes downward because the load also goes downward. Okay? If I may draw the arrow here, since the load is going downward or negative, then the line here also goes downward. This is first degree curve. And then when it reaches here, this one will be deducted by the area of this load diagram. And what is the area of the load diagram? Area of the load diagram is W, which is the height of this load, times L. So WUL. That is the area of this load diagram. So therefore, WL over 2 minus WL, okay, WUL over 2 minus the area, which is WUL, that will be equal to WUL over 2. So hence this location here. And then it goes up by a value of WUL over 2 also because of this reaction. So it becomes 0 here. And this is now your shear diagram. Okay? So to solve for the moment diagram is simply, or the value of the moment is simply the area of the shear to the left of it. Okay, the area of the shear to the left of it. So here, since there's no area to the left, the moment here is 0. When it goes to the center, this is a first degree curve, so this will be a second degree curve. Second degree curve, like that. Okay? And the value here is the value of the area of the shear to the left of it. So this one is a triangle, so 1/2 base. What is base? L over 2 times height. And the height is WL over 2. So WUL over 2. Hence, you have this value of 2 times 2 times 2, that will be 8. So WUL squared over 8. Okay? Then, this one is a negative area, so it goes down by the same magnitude of the area but negative until it becomes 0 here. Okay? So that is how to draw the shear and moment diagram and solve for the maximum moment. So the maximum moment is WL squared over 8. So going back here, use WL squared over 8 and you can generate this answer. Just make sure the units are in foot and kip. Okay, so that is the first and second part. We now go to step number 3. Step number 3 is compute for steel ratio and assume that the beam is tension controlled. So if you assume the beam is tension controlled, the strength reduction factor is automatically 0.9. And then try to recall these standard ACI formulas. We have the formula for computed steel ratio and the formula for coefficient of resistance, or Rn. So let's first solve for Rn using this formula. Plug in the value for mu, plug in the value for phi, which is 0.9, and b 16, and d is a decimal place, which is 29.56 squared. Just make sure that the units of mu are converted back into pounds and inches. Okay, so that you can get a unit of PSI. So therefore, this mu here, multiply it by 12 and 1000. Okay? So you get this value. Next is to compute for the computed steel ratio with this formula. After solving for Rn, you can plug in the value of Rn here and then solve this equation. Fc prime is given, Fy is given, Fc prime is given. You can solve the whole equation and this will be the answer. Okay? So that is your step number 3. Step number 4 is to solve for the steel area. Now, steel area is given by this formula. AS is rho times B times D. And rho is the computed steel ratio here. You plug in this value to this. And then your BD, your assumed value for B, which is 16, and D is 29.56. And you can generate this answer. Okay? So, if we go back to the question, we already have this B, we already have this H, and we have this AS. But we are required for the number 9 steel bars. Okay, number 9. We are going to use the number 9 steel bars. So how do we do that? We have to do a trial and error. Okay, trial and error. The number of bar is number 9, or the bar number is number 9, and the quantity, okay, let me just change this one to quantity so that you will not be confused. The quantity of bars is 5 pieces. Okay, so how do I know 5 pieces? Let me demonstrate. If this is your beam and this is your stirrups, this will be your main bars. Alright. The standard covering here is 1 1/2. Okay, 1 1/2 inch. This one is 3/8 of an inch. And the standard spacing here, based on the code, is 1 inch. Okay? So, the question is, will the number of bars here fit to this B, which is computed at, or which is estimated at 16 inches in the first few steps? Okay? So, let's try. If we try 2 pieces, okay, this is having a formula already, so it will just comment here, the red marks here, it will comment if it's not okay. Let's say if you have 8 pieces, it will say not okay. Why? Because if you have 8 pieces, it will not fit into this beam. Okay? It will not fit. Because if you have 18 inches, the total width now of your beam will be 19 3/4. Okay? If you plug in 7 pieces, the total width of the beam will be 17.58, still not 16. If you plug in 6 pieces, that will be 15.5. Okay. But the problem is the total area will be very much higher than the required steel area, which is we have computed at 4.19. Let's try 5. If we try 5, the total area will be 4.97, a little higher than 4.19. If we go for 3.98 versus 4.19, it will not be okay, meaning the total area that you have specified 4 pieces of number 9 is lesser than the required area. So we have no choice but to use 5. Okay? So, yeah, to determine the total width, just do like this, 1.5. So 1.5 times 2, because there are two coverings, left and right, plus we have the stirrup, so 3/8 times 2 again, because there are two stirrups here. Let me shade, no? Two legs of the stirrups. Okay? Then plus the number of bars, so n times number 9. The diameter of number 9 is 1 and 1/8. Okay? Because number 9 is 9/8. And 9/8 is 1 and 1/8. So n times 1 and 1/8 plus this one. If this is 5 pieces, there will be 4 spaces. Okay? So therefore, we can have n minus 1. Okay? If this is 4, there will be 3 spacings. If this is 3, there will be 2 spacings. That's why this is always n minus 1. So n minus 1 times 1 inch. Okay? So just plug in the number of pieces, quantity of bars, and here is the quantity of bars, until you can get a value of, let's say for this 5 pieces, that will be 13 and 3/8. Okay, if 5 pieces. Okay, so it satisfied that the total area for the 5 pieces of number 9 is greater than the required, as well as the width of the beam is below the assumed width, which is 16 inches. So this is okay and okay. Next, check the steel ratio in terms of code requirements. Okay, you have previously have your steel ratio 0.008, but this is still temporary. This is just to get the required AS. You have now a new AS based on the 5 pieces of number 9. So your new AS will be the AS actual, and that will be the raw actual, AS actual number 9, or 1 and 1/8, so pi d squared over 4, and your d is 1 and 1/8 times 5, because there are 5 pieces, and you can get this value. Next is the raw actual. The raw actual is AS actual over BD, and you can get this value. After that, you can now solve for the upper limits, the upper limit and the lower limit. So for the lower limit, the minimum steel ratio is the bigger of the two. 3 times square root of FC prime over Fy, and 200 over Fy. So here, the answer is 0.00316 and 0.00333. And of course, the governing steel ratio is the bigger of the two, which is 0.00333. And then you also solve for the maximum steel ratio. The maximum steel ratio, to solve that, we need the C maximum, the A maximum. Okay? And C maximum is 3/8 of D. Okay? So 3/8, simply multiply 3/8 times your D, which is here. This is your D. So D times 3/8, that will be 11.085. And then compute your beta 1 using this formula. And beta 1 can be computed if your FC prime is 4,000, the value is 0.85. And then A is beta 1 times C. So 11.085 times 0.85, that will be 9.42 inches. Next is, you can now compute for the maximum steel ratio, and that is having the formula rho max is equal to 0.85 times A times FC prime divided by FYD. So plugging in all the values, and the value for A, you plug it in here, you can get this value. So the actual, rho actual, should always be lesser than or equal to the maximum, and should be greater than or equal to the minimum. Okay? If this is not satisfied, then you change your design. Okay? You upgrade, you add more steel, or you deduct some steel, depending on what happens here. If above maximum, you deduct the quantity of steel, or you increase the width, whatever, as long as the rho actual should be within the minimum and maximum. Here in my Excel file, there is a formula here that will automatically state if the steel ratio is within the bounds of the minimum and maximum. In short, within limits. Okay, so our steel ratio is good, and we are now ready to check the moment capacity. Okay, so to check the moment capacity, first we have to determine the depth of compression stress block, and it is having this formula ASFY divided by 0.85 FC prime times B. Okay, and this AS will be your AS actual. Okay, always remember actual, because we have already identified that the quantity of bars that we are going to use is 5. So that will be your actual. Okay, so plugging in the values, you can generate this answer. And thus, you can also solve for C, because C is simply A over beta 1. Then after that, you check the strain in steel. Check if it is tension controlled, or compression controlled, or transition controlled. Okay, anything above 0.5 is tension controlled, anything below 0.2 is compression controlled, and between 0.4 and 0.004 and 0.005, that will be your transition controlled. Okay, then if tension controlled, automatically your phi is 0.9. If compression controlled, automatically that is not permitted by the code. And if the value is between 0.4 and 0.5, the value of your ES, then use this formula. Okay, in my Excel file, the formula is this, and you can pause the video to copy or to investigate this formula. Alright, so by the way, the tension controlled has this formula also. It will say tension controlled, transition controlled, or compression controlled, and not permitted, depending on what the value of your strain in steel is. Okay, so after that, we now know the phi, we now know the A, therefore we can solve the nominal moment capacity of the section. Okay, so nominal moment capacity is, if you can recall, that will be simply equal to the force, whether tension or compression, times the moment arm, which is D minus A over 2. And T, we know T is AS Fy. Okay, so AS Fy times D minus A over 2. The A that you are going to use is this. Alright, so plugging in the values, you can generate this answer in pound inch. And then divide it by 12,000, you can generate kip foot. And the ultimate moment capacity, Phi-Mn, is now 599.88 because this one is multiplied by 0.9. Okay? This value here, the 666, will be multiplied by 0.9. So it will generate 599.88 kip foot. Okay? And the section will say satisfactory. Why? Because 599.88 is more than the computed or the required moment, which is 513.76. 599 is greater than 513. Okay? Now, let's say for the sake of further discussion, let's say you have only computed 4 bars. It will say here redesign. Okay, because 489.71 is obviously lower than the required, which is 513.76. Okay, although it passed the width because the required width is only 11 and 1/4, but it did not pass the required total area of rebar. Okay, so I hope you learned something from this discussion. Have a good day.